Okay, this is correct title. The motivation of our study was very simple. We tried to find a difference, to find an impact of the special inversion symmetry by playing with the same elements in the closed compounds. So the research was done by a large group of my colleagues who were responsible for who did simple sample growth, optical measurements, specific heat measurements, Andreev spectroscopy, thermodynamics, ARPIS data in Moscow and in St. Petersburg and in UK, and theorists who calculated the results. And this is not the end of the list. We also collaborated with the theorists from Graz University, from Graz University of Austria, and did measurements at ultra-low temperatures using the scanning tunneling microscopy. Okay, so here is the motivation of what you already pronounced. We were interested to investigate the impact of the inversion symmetry. Impact of the inversion symmetry on the compound superconductivity in neighboring compounds. So there are known examples of non-central symmetric superconductors such as listed here. Cadmium arsenide, strontium 122 material, natrium, sodium 122 material, tantalum arsenic, iodine arsenide, bismuth, palladium, and so on. So, particularly in this field, there were some interesting features were found in the superconductivity. And theoretically, the idea is behind this inversion symmetry is as follows. When you have inversion symmetry lacking, then non-uniform lattice potential, which is sensed by conduction electrons, it split the spin up and spin down energy bands like a Rashba effect. And the two electrons forming the Cooper pair, they becomes belonging to a different Fermi surface corresponding to the spin up and spin down subbands. And this can lead or may lead to quite interesting consequences predicted to mixing of the spin singlet and spin triplet pair and components. The resulting exotic states, according to theory, might have a different mixture. So we were actually interested to find signatures of physics, which is highlighted here in blue. So we have chosen the two components of the tin and arsenic, and the first one is central symmetric. It has a space group Fm3m. It is shown here, the very simple sodium chloride type structure, FCC, and this cartoon refers to the textbook physics, but irrelevant to the tin arsenide. It illustrates that when the electron field moves somewhere away of the gamma point in the brilliant zone, it may feel a gradient of the potential, and this gradient of the potential lead to the Rashba effect, split the energy band because of the effective field associated with the Lorentz transformation. Now, this is just textbook physics to illustrate what we were searching for. Now the measurements were done. First, the band structure was done with the ARPIS machine in laboratory, and then on in St. Petersburg and in Moscow. The band structure is rather simple. it is nicely consistent with calculated band structure. It consists of electron bands in and hole bands in the gamma point. So here are the Fermi surface corresponding to the zero energy of this calculated band structure. And we studied in experiment this this tiny range of energies, because we did measurements with the laboratory photon source of helium lamp. It's important to say that the calculated band structure is more sensitive to the, is slightly sensitive to the true spin orbit true spin orbit coupling for different orbitals, but is very sensitive to the bulk or slab shape of the of the studied samples, investigated samples. The energy band structure close to the gamma point is well identified. It's fully consistent with theoretical calculations, and so we move to transport measurements. In transport measurements, we see a sharp superconducting transition, and we focus on the specific heat measurements, which could be traced as a function of magnetic field. The magnetic field suppresses the transition and shifts it to the lower temperature side. It can be analyzed and calculated the height of the specific heat jump. From these measurements, we can plot the TC versus magnetic field plot, which doesn't show any nothing specific. And from Andreev reflection spectroscopy, we also trace the evolution of the superconducting gap as a function of temperature, and we didn't see any substantial deviation from the BCL theory. Now, we move to more interesting compound, which is made of the same elements, tin and arsenide, but it has non-central symmetric structure and space group R3M with a hexagonal unit cell. There are actually several different positions of tin, which may be traced here. Therefore, the primitive lattice is rather large. And the topography by scanning tunneling macroscopy reveals similarity to the structure, to the textbook structure, and there are some defects may be found as tin vacancies in different layers. The ARPIS measured band structure is illustrated here. It shows different bands which have proper symmetry at different values of the momentum. They can be identified with different orbitals. So the result is very nicely consistent with theoretical calculations, and the total Fermi surface look like this. Now we focus on the specific heat again. Temperature depends on the specific heat, shows the sharp drop, which can be analyzed, and lattice and phonons and electron contributions are separated. We again find that the amplitude of the specific heat gap is very close to that in the BCS theory. The temperature depends on the magnetic field. is also consistent with the BCS theory, and 2 delta over TC ratio is just coincide with that in BCS. I didn't put here a plus minus sign, but it is just like a textbook value. We also tried to see anything interesting in local density of states by scanning tunneling spectroscopy, doing this down to 50 millikelvin. And we find a fully formed gap, which is spatially uniform, no nodes, and the shape is characteristic of isotropic S-wave superconducting gap. So all these features which I have shown, they indicate the type 1 superconductivity in both compounds with no deviations from the BCS. Just to apply a final comparison whether this material is a type 1 or type 2 superconductor, we plotted the figure like this, which is a figure like this, where we plotted the difference of the specific heat as a function of the temperature, and for all these, for all type 1 superconductors, known superconductors, it can be calculated from the critical temperature and derivative of the critical magnetic field at critical temperature. So you see that all type 1 superconductors nicely follow this behavior. And our 2 materials which we studied, tin for arsenic 3 and tin arsenide, also belong this line. So we conclude that these are 2 types of the they belong to the type 1 superconductors, both. And we conclude the anticipated impact of the presence or absent reversal symmetry is missing in this compound. And for both, there is a nice agreement with the weak coupling BCR theory. We didn't find any unconventional superconducting properties in both spin orbit and spin orbit missing materials. No signatures of either mixed type superconducting pairing or multi-gap superconductivity we found. It means that the more deep theoretical calculation, theoretical analysis required to reveal this, reveal the impact of this spin orbit coupling on superconductivity, on mixed type superconductivity. Thank you for your attention.
Thank you very much. I'm very much interested in these systems. I also measured the point contrast spectroscopy in the, I think, molybdenum, aluminum 3, carbon 2 or something. I don't remember exactly, but I had the same results. So despite the fact that it was a non-centrosymmetric, we found a perfectly BCS behavior and nothing strange. So the question is, since you have been working on this, are you aware of a system in which instead the spin orbit of this kind, I mean, in which there are evidences of mixed pairing?
The spin orbit coupling is something which comes from this layers, so we cannot check it. We for sure know how it is. Yes. Then we we know the band structure, now where electrons are moving, so which potential they feel. So we can calculate, and we do calculate the spin orbit coupling impact on the band structure. That's what we know. But how it affects the superconducting properties, we do not know. We were actually searching for this, and we didn't find it.
There is some compound that has been shown to be known.
It was claimed, at least. It was claimed in the literature.